Okay, we're going to take a look at if we were building triangles of different sizes. This doesn't change our trig ratio, so I don't want you guys to think that what we taught you about unit circle is incorrect, but what I'm hoping, a question that maybe you came up with is, how can we use just the unit circle? What if we change the size of the circle? Then does that change things like the sine, cosine, and tangent ratio? So how is it okay that we just use the unit circle? And remember, in mathematics, we usually don't have something just because someone decided it's that way. It usually has some rationale behind it. So to look at this rationale, we're going to look at a couple of patterns that we can see here. So I'm going to start by looking at this triangle. So we said this was a 30, 60, 90. So I'm going to fill that in here, where the short leg is 5, the other leg is 5 rad 3, and the hypotenuse is 10. And at first, we're going to focus on the 30-degree angle. So if we focus on the 30-degree angle, and we're going to fill in these ratios here, sine, cosine, and tangent of 30 degrees, specifically of this triangle. So remember, sine opposite over hypotenuse would be 5 over 10, which would reduce to 1/2. Oops, there we go. And then the cosine of 30 would be the adjacent over the hypotenuse, which would reduce to rad 3 over 2. And the tangent of 30 would be the opposite over the adjacent, which would reduce to 1 over rad 3. And we've rationalized this now several times and seen that that's the same value as rad 3 over 3. Now if we change our perspective to the 60-degree angle, if we do the sine now, which would be opposite over hypotenuse, we get that the sine of 60 is rad 3 over 2. For the cosine, we would do adjacent over hypotenuse, and we see that the cosine is 1/2. And for the tangent, we would do opposite over adjacent, and we would get rad 3. Okay. So those numbers should look a little bit familiar. And now I'm going to show you what if we decided to have built this other triangle instead. What if I built a much larger 30, 60, 90 triangle where across from the 30-degree angle was a side length of 12, then the other side would be 12 rad 3, and the hypotenuse would be 24. So if I go through again and focus on the 30-degree angle and do the same calculations as before, the 30-degree angle would have a sine of opposite over hypotenuse, which reduces to 1/2, a cosine of adjacent over hypotenuse, which reduces to rad 3 over 2, and a tangent of opposite over adjacent, which reduces to 1 over rad 3, and we know can be rationalized to rad 3 over 3. If I change my focus to the 60-degree angle in this triangle, if I find the sine, that would be opposite over hypotenuse, which would reduce to rad 3 over 2, adjacent over hypotenuse, which would reduce to 1/2, and tangent, which would be opposite over adjacent, which would reduce to rad 3. Notice that we got all the same values for each of those triangles. Okay, so what I'm going to do now is build the most generic form of a 30, 60, 90 triangle. I'm not going to give it any size. I'm just going to fill in the relationship that if the short leg is n, the other leg is n rad 3, and the hypotenuse must be 2n. So that's kind of looking at this idea here. Now, if I again go through and calculate these ratios, and I focus on 30, the sine of 30 would be n over 2n, which would reduce to 1/2. The cosine of 30 would be n rad 3 over 2n, which would reduce to rad 3 over 2. The tangent of 30 would be n over n rad 3, which would reduce to 1 over rad 3, and again could be rationalized to look like rad 3 over 3. If we changed our perspective to the 60-degree angle, we would have opposite over adjacent, so the sine would be rad 3 over 2. Adjacent, sorry, I meant when we set up the sine, I said it incorrectly as we set it up, but it was opposite over hypotenuse. For the cosine, adjacent over hypotenuse would give us 1/2, And for the tangent, we would do opposite over adjacent, and we would have rad 3. So notice it didn't even matter that the n was there. That factor was canceled out in each of our ratios, and we got the same answers for every single scenario. You can see the same thing happen in your 45, 45, 90s. Instead of making you go through the whole list, I'm just going to show you the ratios we get one time with n. So this is our 45, 45, 90. You can pick either of the 45-degree angles. So sine would be opposite over hypotenuse, which would be 1 over rad 2, which gets rationalized to be rad 2 over 2. Cosine would be adjacent over hypotenuse, which would yield the same answer as before. And tangent would be opposite over adjacent, which would give us 1. So the point being here that n doesn't represent any size. You could use any value in there, and you notice that you get the same answers that you got in all of the other instances. So what this tells us is it doesn't matter how large the triangle is, the trig ratio does work out to be the same value no matter the size of the triangle. Since the triangles are how we got the coordinates around our circle, that means it doesn't matter the size of our circle either. So when we look at this conclusion statement down at the bottom, we are saying as sides of triangles are enlarged, this should say they grow proportionally. So what proportionally means is that if one side of the triangle triples to make a bigger version of the triangle, all of the other sides triple as well. Since trig functions calculate a ratio, this means what? So again, what we just looked at, and I'm just going to give you guys a new generic triangle that's not necessarily a 30, 60, 90 or a 45, 45, 90. Let's say you had some angle in this triangle, and you calculated the sine of that angle in this triangle, and you got 5 over 8. If the triangle grew proportionally, so the sides all got bigger with the same type of factor, so let's say this became 15, then this side would be 24 because they're getting multiplied by 3, and here would be our angle. It's the same angle. When we calculate sine of the angle, notice we get 15 over 24, but what really is 15 over 24? 15 over 24, we can see these values of 3 cancel out, and we're again left with 5 over 8. So what we see here is that since the trig functions calculate a ratio, this means that the ratio will always be the same. That we're going to see it always reduce down to the same value no matter how big the circle. This means it doesn't matter what size the circle. If we drew circles with radius of 1 or 2 or 5 and marked these special angles, we would all get the same sines, cosines, and tangents, even though our coordinates would be different, because our sine, cosines, and tangents take 2 coordinates and divide them, and they cancel out that extra factor. So why did mathematicians choose a unit circle? Remember, they like simplicity, and you might not think that the numbers there are simple, but because they chose a radius of 1, that means they don't have to cancel out any of those extra factors. So they would already consider what they have in simplest form. Okay? So the homework that goes with this tonight is not a new concept. This was just to solidify the idea that the unit circle is okay to use and to make sure those questions are addressed if you had any about why is it okay to just use this one type of organizer. It's really the same as using any other size. So you're just going to go back through tonight and work on making sure that you remember how to calculate sine, cosine, tangent, cosecant, secant, and cotangent of any of the angles around the circle.